The most brilliant minds in the scientific community have long been perplexed by certain phenomena. But what exactly are these phenomena? Do they indicate the presence of intelligent life on other planets? Join us as we delve into the James Webb Space Telescope's startling discovery of potential city lights that could alter our understanding of the universe. To date, Earth is the only planet known to harbor life. Since the dawn of civilization, humanity has wondered if life exists elsewhere in the cosmos. In an effort to address this question, American astronomers Jill Tarter and Thomas Pearson initiated the search for extraterrestrial intelligence, SETI, project in 1984. This nonprofit initiative aims to detect spaceborne radio signals, which are more likely to be picked up by the 42 radio telescopes that make up the Allen Telescope Array in California's Cascade Mountains. Radio waves are preferred due to their ability to travel vast distances with less dispersion compared to other types of radiation. However, despite 30 years of searching, no verifiable alien signals have been found. The James Webb Space Telescope, which was successfully launched to aid this quest, is now examining distant, undiscovered planets orbiting far-off stars. As the world's largest telescope, situated about 1 million miles from Earth and equipped with highly sensitive detectors, it is poised to make groundbreaking discoveries. 20 years ago, planets beyond our solar system were unknown. Since then, over 4,000 exoplanets have been discovered orbiting other stars. NASA estimates that there may be trillions of exoplanets in the universe. The earliest signs of extraterrestrial life might come from detecting plant life on distant worlds. For example, the Galileo spacecraft, on its route to Jupiter, observed a clear indication of plants on Earth through the detection of the vegetation red edge, VRE, biosignature, a combination of red and infrared light reflected by plants. A planet covered in vegetation akin to Earth's jungles would emit a strong VRE signal. The JWST will measure VRE on distant Earth-like planets within the habitable zone around stars, which could provide crucial clues about life in their atmospheres. By analyzing the light passing through a planet's atmosphere when it crosses in front of its star, the JWST can identify missing wavelengths via spectroscopy. The specific absorption of wavelengths by atmospheric atoms and molecules creates a unique fingerprint that the JWST can detect, allowing scientists to infer atmospheric composition and the potential for life. Earth-sized planets with atmospheres rich in oxygen, nitrogen, and carbon dioxide are considered good candidates for life. Detecting technological life might involve finding chemicals like chlorofluorocarbons, CFCs, which would be evident from Earth's atmosphere if observed from afar. The presence of such chemicals would suggest a civilization. Life on exoplanets might differ significantly from life on Earth. Extremophiles on Earth, such as bacteria that survive extreme heat, cold, or acidity, illustrate the diversity of life forms that could exist elsewhere. However, planets with extreme temperatures or acidic conditions are less likely to support life compared to those with more temperate climates. Prime candidates for life-supporting planets would have temperatures conducive to liquid water and orbit-stable stars. While our Sun is a yellow G-type star, red dwarf stars, which are more common and cooler, offer a better chance of studying planets with longer lifespans, allowing more time for life to evolve. The JWST's initial mission will focus on the TRAPPIST-1 planetary system, which revolves around a calm red dwarf star and has 7 Earth-sized rocky planets. 3 of these planets are in the habitable zone, where liquid water might exist. Proxima Centauri, a red dwarf star 4.25 light-years from the Sun, is another candidate for finding potential city lights beyond our solar system. Proxima Centauri is about 600 times fainter than the Sun, so a planet must be much closer to it to have conditions suitable for life. In August 2016, astronomers discovered Proxima B, a planet in the habitable zone of Proxima Centauri. Proxima B, with a mass 1.3 times that of Earth, is in the Goldilocks zone where conditions might allow liquid water to exist. However, Proxima B's close orbit, just 4.6 million miles from its star, exposes it to intense solar winds that could strip away its atmosphere. It is also believed to be tidally locked, meaning one side always faces the star, while the other remains in perpetual darkness. This could lead to extreme temperature differences. Proxima B's surface temperature might vary significantly between day and night, which could be indicative of its atmospheric properties. The JWST will measure infrared radiation from both sides of Proxima B to determine if an atmosphere is present. If Proxima B has an atmosphere, analyzing its composition for gases like oxygen, water vapor, and methane could suggest habitable conditions. Yet, the JWST has limitations in detecting unbound oxygen, a strong sign of life. Future ground-based observatories, such as the extremely large telescope scheduled for the mid-2020s, might provide more comprehensive atmospheric analyses. Until then, the JWST's findings will be instrumental in shaping our understanding of exoplanetary atmospheres and the potential for life. Future space telescopes may employ advanced techniques to block out the overwhelming light from host stars and better observe light reflected from planets. This approach could enhance our ability to detect distant planetary features. Nevertheless, many gases produced by life on Earth can also be generated by non-biological processes, such as methane from both cows and volcanoes. Accurate detection of alien life will require discerning between biosignatures and other processes. As astronomers continue to explore, they may encounter false positives and must thoroughly analyze planetary conditions to confirm the presence of life. The James Webb Space Telescope's preliminary data offers a glimpse into future discoveries. Whether life exists elsewhere in the universe remains one of science's most compelling questions. The answer could reveal whether life is widespread across the cosmos or if Earth is truly alone in the vast expanse of space. Both scenarios would necessitate profound philosophical and psychological adjustments for humanity. The most brilliant minds in the scientific community have been baffled by this phenomenon. But what exactly is it? Do these mysterious lights indicate the presence of intelligent life on another planet? Join us as we delve into the startling discovery made by the James Webb Space Telescope, revealing city lights that could change our understanding of the universe. The only known life in the universe is currently found on Earth. Yet, for centuries, humans have pondered the possibility of life beyond our planet. To address this age-old question, American astronomers Jill Tarter and Thomas Pearson initiated the search for extraterrestrial intelligence, SETI, in 1984. This non-profit organization aims to detect signals from space, focusing on radio waves because they can travel vast distances with less dispersion or absorption compared to other types of radiation. Despite 3 decades of dedicated research, no confirmed alien signals have been identified. However, the successful launch of the James Webb Space Telescope has breathed new life into this quest. Positioned about 1 million miles from Earth, this enormous telescope, equipped with highly sensitive instruments, is tasked with examining a multitude of distant, previously undiscovered planets orbiting stars far from our solar system. 20 years ago, we were unaware of any planets beyond those in our own solar system. But since then, more than 4,000 exoplanets have been discovered. NASA estimates that the universe may host trillions of such planets. The first clues to life beyond our solar system might come from extraterrestrial plant life. For instance, the Galileo spacecraft, while en route to Jupiter, turned its instruments back toward Earth and detected a clear sign of vegetation through the vegetation red edge, VRE, biosignature, a combination of red and infrared light reflected by plants. If an Earth-like planet were covered in dense jungle, it would exhibit a strong detectable VRE signal. The James Webb Space Telescope, JWST, is set to measure the VRE of distant Earth-like planets located within the habitable zones of their stars. These signs could be critical indicators of life within the atmospheres of exoplanets. When a planet passes in front of its star, the JWST may detect the light as it enters the planet's atmosphere. Spectroscopy would then reveal any missing wavelengths in the light as atoms and molecules in the atmosphere absorb specific wavelengths, creating a unique fingerprint that the JWST can identify. This method can be used to analyze the atmosphere's composition and determine if conditions might support life. Earth-sized planets with atmospheres similar to ours, rich in oxygen, nitrogen, and carbon dioxide, are likely candidates for life. By searching for elements that are uncommon, we might detect signs of technological life. For example, chlorofluorocarbons, CFCs, used in refrigeration and cleaning products would stand out if detected in the atmosphere of another planet. just as they would if extraterrestrials monitored Earth's atmosphere from afar. Interestingly, life on exoplanets might not resemble Earth's life at all. Even on Earth, some organisms, especially extremophiles, microbes that thrive in environments too extreme for most life, can seem alien. Some can survive in temperatures as high as 250 degrees Fahrenheit, while others endure extreme cold, high acidity, or even toxic environments. Despite these possibilities, Earth-like planets are more likely to harbor life than those with extreme conditions. The best candidates for life may be planets with stable stars and surface temperatures that allow liquid water to exist. Our Sun, a yellow G-type star, is relatively rare and has a shorter lifespan compared to other types of stars. Red dwarf stars, more common and with longer lifespans, provide more time for life to develop and evolve into complex organisms. The JWST's first mission will focus on the TRAPPIST-1 system, located about 40 light-years from Earth. This planetary system, orbiting a calm red dwarf star, includes 7 Earth-sized rocky planets, 3 of which are within the habitable zone where liquid water might exist. Despite being smaller and cooler than our Sun, the TRAPPIST-1 star emits light that could support life on these planets. The closest opportunity to observe city lights outside our solar system comes from Proxima Centauri, a red dwarf star 4.25 light-years from the Sun and our nearest stellar neighbor. In 2016, astronomers discovered a planet, Proxima B, within this star's habitable zone. Although Proxima B is only 4.6 million miles from its star, a much closer distance than Earth is to the Sun, it might still support life despite being bombarded with high-energy radiation from frequent stellar flares. Proxima B is thought to be tidally locked, meaning one side constantly faces its star, creating permanent day and night sides with extreme temperature differences. Despite these challenges, if Proxima B has an atmosphere, it might sustain liquid water, which is essential for life as we know it. The JWST will search for city lights on Proxima B's night side and measure the infrared radiation emitted by the planet to determine whether it has an atmosphere. If an atmosphere is present, the next step will be to analyze its composition, looking for gases like oxygen, water vapor, and methane, which could indicate habitable conditions or even living organisms. Even though the JWST wasn't specifically designed to search for extraterrestrial life, it has the potential to make significant discoveries by detecting changes in atmospheric gases. However, it can't detect unbound oxygen, which is the strongest indicator of life. Future ground-based observatories, like the extremely large telescope set to begin operations in the mid-2020s, will conduct more detailed atmospheric studies. The JWST may be able to detect ozone, another key indicator of life. Until those telescopes become operational, the James Webb Space Telescope's early data offers a glimpse into the future of exoplanet research. If life exists elsewhere in the universe, finding it is one of science's most profound quests. Whether life is abundant or we are alone, the discovery will have deep philosophical and psychological implications for humanity. As we await these groundbreaking discoveries, we continue to explore the universe, driven by the hope of answering the question: are we alone in the cosmos? As humanity continues its quest to understand the cosmos, new technologies and methodologies are enhancing our ability to detect signs of life beyond Earth. One of the most promising advancements is the use of specialized spectrographs in future space missions. These instruments will be designed to capture and analyze the light from distant exoplanets with unprecedented precision. By examining the light from these planets, scientists hope to identify subtle chemical signatures that might indicate the presence of life. For example, the detection of unusual chemical combinations or periodic changes in atmospheric composition could provide clues about biological processes occurring on these distant worlds. Another intriguing approach involves the study of exoplanetary moons. Many of the exoplanets discovered so far have been found orbiting around stars that are significantly older than our Sun. These stars have stable, long-lasting planetary systems, and their planets might host moons with environments conducive to life. Moons such as Europa, one of Jupiter's satellites, or Enceladus, a moon of Saturn, have already shown promise for hosting life within our own solar system due to their subsurface oceans. Studying similar moons around exoplanets could expand our search for life to these secondary bodies, which may offer even more diverse habitats. Astrobiologists are also exploring the potential of using machine learning algorithms to analyze the vast amounts of data collected by telescopes and space missions. These algorithms can identify patterns and anomalies in data that might elude human researchers. Machine learning could enhance the efficiency of sifting through signals and spectra, potentially speeding up the discovery process. By training these algorithms on known biosignatures and atmospheric data from Earth and other planets, researchers can improve their ability to detect similar signs in the data from distant worlds. The search for extraterrestrial life is not limited to passive observation. Active experiments are also being planned. One such initiative involves sending small probes to the nearest star systems. Although these probes would take decades or even centuries to reach their destinations, they could carry instruments designed to analyze the atmospheres of exoplanets up close. Such missions would provide direct data on atmospheric composition and potential biosignatures, offering a more detailed and immediate understanding of these distant worlds. In addition to technological advancements, international collaborations are playing a crucial role in the search for extraterrestrial life. The global scientific community is coming together to share data, resources, and expertise. Collaborative projects such as the Breakthrough Listen initiative, which aims to scan the entire sky for signals from extraterrestrial civilizations, benefit from the collective efforts of scientists, engineers, and institutions worldwide. By pooling resources and knowledge, these collaborations enhance our ability to explore the universe and increase the likelihood of making groundbreaking discoveries. The potential implications of discovering extraterrestrial life extend beyond science. Such a discovery would have profound effects on philosophy, religion, and society. Philosophically, it would challenge our understanding of humanity's place in the universe and raise questions about the uniqueness of life on Earth. Religiously, it might prompt new interpretations of sacred texts and beliefs about the origins and nature of life. Socially, the confirmation of extraterrestrial life could inspire new discussions about our responsibilities as a species and how we interact with other potential life forms. Ethical considerations are also paramount in the exploration of extraterrestrial life. As we venture into the cosmos, we must ensure that our activities do not inadvertently harm potential extraterrestrial ecosystems. The planetary protection protocols currently in place aim to prevent contamination of other planets and moons by Earth-based organisms. Similarly, if we detect signs of life, it will be crucial to approach any potential contact with caution and respect, considering the possible consequences for both humanity and the extraterrestrial life forms. As we continue to explore the universe, the question of whether we are alone remains one of the most profound and intriguing inquiries of our time. The search for extraterrestrial life is driven by our innate curiosity and the desire to understand our place in the cosmos. Each new discovery, whether it be a potential biosignature or a new technology, brings us closer to answering this fundamental question. The journey to uncover the mysteries of the universe is a testament to human ingenuity and perseverance, and it holds the promise of transformative revelations that could redefine our understanding of life and existence itself. As we look to the future, the field of astrobiology and space exploration will likely continue to evolve, incorporating new technologies and methodologies to enhance our search for life. The combination of advanced telescopes, space missions, machine learning, and international collaboration represents a multifaceted approach to one of humanity's most enduring quests. Whether we ultimately find evidence of life beyond Earth or not, the pursuit itself enriches our knowledge and broadens our perspective, reminding us of the boundless wonders of the universe and the ever-expanding horizons of human exploration.